Hello, my name is Justin Campbell. A little bit about myself before I dive into the presentation. I'm a research engineering scientist assistant employed by the University of Texas at Austin's Computational Research and Ice and Ocean Systems Group, or CREOS for short. The group is part of the university's Odin Institute for Computational Engineering and Sciences, and their mission is to apply advanced computational methods to improve the understanding of the role of the global ocean, sea ice, and ice sheets in the climate system. In particular, Bayesian inverse methods, scientific machine learning, and other computational techniques are used to develop numerical models that can improve the group's mechanistic understanding of current and predict future ocean phenomena. One such climate model is the Massachusetts Institute of Technology's General Circulation Model, or MITgcm for short. As the name suggests, the model is used to study oceanic and atmospheric phenomena using finite element methods, and is a community model with open source code where hundreds of researchers and scientists have contributed to the model. As part of the project entitled Estimating the Circulation and Climate of the Ocean, or ECHO for short, this MITgcm model output is assimilated with remote observational data from satellites and in situ observational data from cruise ships and Argo floats, among other forms of measurement, to produce a time evolving estimate of atmospheric and ocean circulation properties. Now, this project involves the development of post-processing and data analysis routines that are geared specifically towards operating on model output data of the format that MITgcm produces. Now, my responsibilities as a research engineering scientist assistant involve contributing to the development of data analysis and climate model simulation workflows. And as part of the latter, bottlenecks in MITgcm model users' workflows, both within the group and in the larger community, have motivated the undertaking of this project to develop portable units of software that can automate much of the workflow of setting model problem specifications, building and running model experiments using MITgcm software, and ultimately interpreting the results using Echo software. Ideally, these products will reduce the time and energy needed for an end user to execute this workflow for the research using this model, which has been in development for a significant amount of time and is not going away. So the underlying problem statement that motivates this project um, was in part inspired by conversations with research engineering associates and graduate student researchers within my organization, namely Ivana, Helen, and Shreyas. Um, so to expand on this problem statement, many scientists, researchers, and other members of the MIT GCM community experience complexity with and time-intensive involvement in configuring access to computing resources and establishing environments for building, running, and ultimately visualizing MIT GCM model problems. Additionally, many users find it inconvenient and time-consuming to read through numerous user guides and tutorials to become familiarized with learning new skill sets to perform the research, such as determining what software modules and libraries to install on their host machine, scheduling job submission scripts, learning new skill sets entirely like shell scripting, navigating Linux environments, and others. It could also be meddlesome for users to perform the post-processing and data science tasks of writing out, importing, wrangling, and visualizing model output data using numerous analysis routines that exist within the MIT GCM and Echo software packages that are always changing. Lastly, many problems developed using MIT GCM can take an unreasonable amount of time to build and run on host architecture and could benefit from a more lightweight execution environment. Given these limitations and inconveniences with building, running, and interpreting MIT GCM model problems, there exists a need for the development of portable units of software that can be used to build and run models in an isolated environment where minimal prior knowledge of software module, library, and other dependency installation and usage are required. These portable units of software would ideally come equipped with a pre-installed operating system along with necessary software modules, libraries, and dependencies needed for the end users to perform all tasks in the MIT GCM Echo workflow. This would effectively reduce the need for the end user to determine what software tools to install and certain skill sets in computing like shell scripting to acquire, along with the need to comprehend analysis routines for post-processing models. Now, these isolated environments would ideally function as a one-stop shop for all MITgcm Echo workflow tasks and as lightweight virtual machines that can run on any host machine with some fundamental limitations that will be talked about later, regardless of that machine's architecture, operating system, etc. So to address the project's needs statement, project objectives have been documented into two categories, namely SMART goals, or concrete goals that are smaller in scale and more achievable. Specifically, SMART stands for specific, measurable, achievable, realistic, and timely. And secondly, stretch goals, namely ambitious goals that expand on or provide enhanced functionality to the concrete goals. The SMART goals are as follows: to develop portable units of software to build and run computationally inexpensive MITgcm model problems or experiments with installation of MITgcm and Echo libraries, and to do this without the MPI libraries or message passing interface libraries. Secondly, to configure support for these units of software on the most frequently used computing platforms, architectures, and operating systems, first according to Krios group users. To document software products in a code repository and image registry, and then ultimately present working prototypes to MITgcm Echo senior research scientists and master repository managers that would be responsible for incorporating these products into the workflow. As it pertains to stretch goals that I plan on implementing, time permitting, and assuming technical compatibility with host architecture. The first involves the implementation of a graphical user interface for end users to input MITgcm model problem parameters and specifications such as step size, spatial and temporal domain boundaries, etc., along with desired post-processing and data analysis tasks, such as invoking Echo to render data visualizations in a GUI. Secondly, to scale up support for MITgcm model problems and Echo visualization tasks to enable more computationally intensive configurations that require additional computing resources, bear greater CPU and or IO load, among other things such as memory footprint. Thirdly, to add support for ASTA regional domain model problems. And then lastly, configure support for the product or products to run on the most widely adopted computing platforms, architectures, and operating systems, according to general purpose MITgcm community use. So general usage outside of the group that I work for at present. So on this slide is a schematic that overviews the design process framework that I'll follow in working on this project. In particular, the framework follows a conventional iterative product design process that begins with the definition of the problem statement, the associated needs statement that have been discussed earlier in the presentation. The next phase of the project to be completed, and that is currently in progress, with the phase documented as understand, which will involve the definition of design requirements, both subjective technical requirements and quantitative requirements, performing background research on software tools that the products in this project will utilize through user guides and literature reviews, and documenting the outcomes of projects that are similar in scope. And lastly, finalizing customer needs, which will involve communicating with other senior research associates and graduate students using the software to get their input on how this product can first be optimized for their collective benefits. Following the understand phase, we have the ideate phase, which will involve the development of sketches and schematics to communicate the flow of information in the product in a hardware, software independent way by defining the product as a black box with inputs and outputs, and identifying each input output in the project and the product and the systems that they communicate with. Then the black box definition of the product will be translated into a hardware software specific product design or designs deemed as preliminary designs and documented. Transitioning to the evaluate phase, the preliminary designs will be iteratively tested, troubleshooted, and working designs will then be checked against requirements to determine whether or not They fit with their strengths and weaknesses enumerated. Requirement, compromise, and decision matrices schematics will then be developed to document trade-offs in the preliminary designs. From here, a decision tool will then be incorporated to rate down selected designs that meet all necessary requirements in a feasibility study in the design, or designs that are the most optimal according to the results of the feasibility study will then be selected as detailed designs to be carried over into the prototype and testing phase. Here, detailed technical drawings and schematics of the detailed designs will be documented, and mathematical and or computational models for the designs will be implemented in their applicable system architecture. Using this information, the physical model of the detailed designs will be built, and an analysis plan will be developed to specify approaches to testing and analyzing the performances of detailed designs according to benchmarks such as compile time and runtime, compute resource allocation, etc. Then the test results of the detailed design prototypes performances will be documented according to this analysis plan. And lastly, requirements verifications will be performed to check that the working product satisfies critical project requirements according to end user and stakeholder expectations. And ultimately, from here, if there are any requirements that are satisfied through the design, it's an iterative process. So I will be running through these steps iteratively until the design does meet these requirements according to the end user and stakeholders. So presented on the slide is a high-level overview of the workflow that I'm undertaking and working on this project. This workflow can be thought of as a working methodology for performing tasks from the understand to the prototype and test phase of the product design process that was mentioned in the previous slide. As an iterative process, the first task involves gathering and verifying requirements and communicating with end users on the project. Since the product's first release will be intended for Krios Group MITgcm users specifically, high-level communication regarding project objectives, design requirements, etc. will be established with my manager or the boss of the group, along with other researchers and graduate students who will benefit most from portability and improved efficiency of compiling and running MITgcm model problems. The next step in the workflow is the system design phase, which will involve developing flowcharts for high-level layers of communication and procedures between product elements, and within these product elements from class diagrams to pseudocode. From here, the diagrams will then be implemented in code. The code will be incorporated into a containerized environment and ultimately tested on a CentOS 7 Linux operating system distribution running on an Oracle VirtualBox hypervisor. And this operating system and the compute resources that this VirtualBox hypervisor comprise will be the initial development environment. Now, this development environment was chosen because of the lack of permissions to run containers directly on the user's, the group's HPC compute resources, namely on Sverdrup, which has about 1,000 compute node cores, and Texas Advanced Computing Center login and compute nodes where Docker is not installed. This brings up the next stage in the workflow, which involves using another containerization software called Singularity that is installed on TAC and Sverdrup compute nodes to build and test Singularity scripts from the runnable containers that are tested in the virtual machine environment. Therefore, the development environment for building and testing Singularity scripts from functional containers will be a CentOS 7 operating system distribution that's natively installed on Sverdrup and Stampede 2's compute nodes. Now, it should be mentioned that the initial goal for the end user environment of the product is to have it running on CentOS 7 on Sverdrup for immediate access by the group. However, as briefly touched upon earlier, stretch goals involve configuring the product to run on Stampede 2 compute nodes and perhaps other Linux distributions and computing architectures used by MITgcm users. In step 8, after the output of the Singularity scripts are checked against their container counterparts in the virtual machine environment, The final product will be pushed up to code and image repositories and ultimately tagged for release to the public. Any recommendations for feature improvements, bug fixes, performance enhancements, etc., will be continuously incorporated in the workflow, bringing us back to step one, shown in this iterative design. And with respect to collaboration on the project, I've established this high-level top-down flowchart to characterize the communication hierarchy and scope of communication with different collaborators on this project. At the beginning of the project, I briefed my manager, Patrick, of the problem and needs statements, along with objectives of the project and my chosen design process. I will establish recurring meetings with him throughout the project lifecycle to brief him on updates as I make progress through designing, testing, and implementing my product or products. Below, I've documented the contact information of two of the research groups, senior research associates, Anna and Helen, with whom I plan on setting up periodic meetings to have high-level discussions about gathering project requirements and product end goals to best address Creos group needs. These high-level discussions will be incorporated into ad hoc meetings with graduate research assistants Ivana, Shreyas, and Matthew around their research schedules to troubleshoot system design errors, validate requirements, and engage the feasibility of system designs. Lastly, time permitting, and addressing the stretch goals to release a product that is compatible with computing hardware and software in the general MITgcm community, and thus not limited to the Creos group specifically. I will establish periodic meetings with senior research scientists with NASA's JPL and O and Ian, who are largely responsible for maintaining the MITgcm and Echo master repositories and an ecosystem. So the next steps in the project design process will involve performing a literature review on the broad subject area of using portable units of software to run climate models in a platform agnostic way, reading through relevant user guides for installing and operating software tools that are applicable to this project, beginning the ideate phase of the project by developing sketches and diagrams that best communicate layers of information in the system design, and lastly, scheduling and incorporating feedback from periodic meetings with project collaborators to gather and check design requirements. And here are the references. Thank you.